All right, so now we move on to lesson 6.2, which is multiplying and dividing rational expressions. Now, in the first section, we're going to primarily start with multiplying, and then for part two, we'll look at dividing and what that looks like. Now, we know whenever we multiply fractions, such as the example that's given to us here, what we can do is we consider numerator to numerator and denominator to denominator, or we can even look across in terms of from one fraction to the other fraction and see what reduces. Now, in the first situation, what I can do is I'm going to reduce each of them in the following way. We know 12 and 4 can eventually reduce down to, and maybe I shouldn't block it all just so you can still see the number. I'm going to put dots over, and if we take 12 over 4, well, that's going to reduce to 3 over 1. And then if we reduce 10 and 5 across the multiplication, this is going to reduce down to 1 and 2, because 5 over 10 is the same as 1 half. Now from here, this is going to give us a fraction equal to, we multiply across the numerator, 3 times 1, which is equal to 3, divided by, in the denominator, 2 times 1, which is 2. Therefore, our answer is 3 over 2. Awesome. Okay, now if we go over to our dividing answer, what we're going to do is we're going to look at this and say, well, from previous grades, we would have learned that we can take this fraction of 3 over 5 and we can change it to being multiplied by, but if we change this from division to multiplication, we must do the reciprocal and take the 20 and put it in the numerator divided by the 15 in the denominator. Now we're going to do that same skill we just did. If I take 3 and I reduce it with the 15, well, 3 over 15, this is the same as 1 over 5. And then in terms of the 20, when we reduce this by 5, this is going to become 4 over 1. Now, when we write this as an equals, we write 1 times 4, which is 4, and we divide this by the 1 times 5 in the denominator. Now, we don't want to forget about the negative. I can put that either in the numerator or denominator because it is transitive, whether it's in the numerator or denominator or even out in front, that's all the same. And we consider negative 4 over 5 to be our answer. All right, now let's go down to the following rational expressions. So we see it as something like this. Well, first and foremost, we want to state our MPV. I think that's really critical here. So we're going to write our MPV right away. And our only MPV is where a cannot equal 0. Because if a is just isolated by itself in this situation, it's cubed. As long as it's not 0, it won't cause this denominator to be 0, and we'll be happy with this. But when we actually look to multiply this, we're going to do the following. We're going to compare and be like, okay, well, we have an a and then an a cubed. What does this reduce to? Well, this reduces in the following way. We can cancel out the a that's here. We can cancel out the 3 and instead write 2. And then we can expand this and say, well, 5 times 1 is going to be 5 in the numerator, divided by, in the denominator, 3 times 4, which is 12, a squared, which was left behind. There's our answer. And again, we always want to state the MPVs before we cancel, just in case it would have eliminated the a or gotten rid of it completely. So really, really important is just make sure you have your non-permissible value and you're good. Okay, we move on to our next example. Again, we're going to want to do the reciprocal rule where we flip this from multiplication to division. So I'm going to do the following. This is going to be x plus 2 and then divided by the 5x that was there. This is now multiplied by 20x in the numerator divided by the 2 times x plus 2 in the denominator. Now, here's where it's a little interesting, is when we look at what our MPVs are, our MPVs for the divisible case is where it's these two that were in the denominator, but it's also this now, because as you see, now the 2x plus, or 2 times x plus 2 is in the denominator, so it's actually that all three of these need to be accounted for in the NPVs. So let's state that right away. If we look at this, we're going to be like, the NPVs are where x cannot equal, first of all, 0, because if x was 0, then it would wipe out the first fraction and make this term 0 in the denominator, which makes it undefined. And then our other MPV is where it cannot equal negative 2, because if it was equal to negative 2, this bracket would go to 0 and make that denominator 0. Also, if x was 0, it would wipe out this term, which would then wipe out this denominator. So we want to almost highlight this, and I recommend you do this. Highlight these three terms because these three are what we use to consider our MPVs. Now what we're going to do is we're going to cancel some terms. So we're going to cancel out our x and our x. We're going to cancel out our x plus 2 and our x plus 2. And then what we're going to do is do our 20 divided by 5. 20 divided by 5 is the same as going 1 and 4 here. So therefore, our answer would also be, I mean, and actually, you know what we could even do is we could do this as 20 divided by, so I'm going to backtrack this just a tad here. I could do this as, and I'm going to take it one step further before I go and do this. So let's just backpedal this all here. There we go. I'm still going to cancel the x plus 2's, so those can go away. I'm still going to cancel the x's, so I'm still satisfied with that. But what I'm going to do to simplify this is I'm going to write it as equal to, we have 20 divided by 5 times 2, which is 10. 20 divided by 10 is the same as this saying it is equal to 2. So there's the answer. And that's why I wanted to backpedal it, just so that we could show that when we actually combine our denominators, it would end up reducing as 20 over 10. Okay, now again, MPV is very, very important. Before you do any sort of cancellation, make sure you state your MPVs. Now, with rational expressions, don't forget to state your non-permissible values, and more importantly, all your non-permissible values. That is the number one thing I would get you to highlight throughout this unit, because realistically, it's half the problem, is stating these MPVs, because you're just demonstrating that you understand that there is gaps in the graph or gaps in the data at these X values. Now, remember that when you cancel across a multiplication sign, this works, but it doesn't work for any other operation. So if you're doing something like division or subtraction or addition, you can't just simply just be like, oh, there's terms across in different fractions, cancel them right away. It only works for multiplication in that way. Lastly, when dividing, we must consider the non-permissible values for all denominators that occur. And that's going to be that secondary line that I want you to highlight, because as we move into part 2, you're going to see that that becomes more critical than ever. Now, something to point out here is that some of you might be tempted to do this within these sorts of units, is go, well, okay, if I'm given the rational expression 3a minus 7 and 3a plus 14, let's just cancel those 3a's because they're the same, and let's just cancel 7 and 14. We can make this 1 over 2, and because there was a negative, it's 1/2. No, that is not correct. This is totally incorrect. So we cannot do this. Similarly, if I was looking at this term here, I can't just be like, oh, x squared and x squared, those cancel. My 2x, hey, look, those cancel. And hey, look, I'm left with 1 over 3. No, this does not work. And I'm even going to put a circle with a line through it, and be like, do not do this. This is not allowed. We can't just selectively choose terms from things being added or subtracted. You can only cancel common terms that are being multiplied to each other. So let's take a look at some examples below in which we look at things which we can cancel because they're being multiplied. So express each product in its simplest form and then state the non-permissible values. Well, first and foremost, I look at this and I'm like, okay, to determine the non-permissible values, which I think is the most important part right away, let's make sure that we go NPV, and maybe we'll do these like somewhat off to the side here. So I'll kind of go like NPV here, and then x cannot equal. Well, one of the MPVs is that x can't be 0, or else it's going to take away this term here. So I'm going to write it cannot be 0. The other one comes from the inside of the brackets. If I isolate 1 minus 2x for being equal to 0, and then I solve it, I'm going to get 1 minus 2x equals 0. I add the 2 across. I'm going to end up getting that if x equals 1/2, this will also eliminate this, which should make sense. 2 times 1/2 is 1. 1 minus 1 is 0, and so that would get rid of this. So now that we have our MPVs, let's work on simplifying this. So I'm going to write is equal to, in the numerator, I'm going to write this as 4x cubed, 2x minus 1 in the numerator. Now, in the denominator, we see that we have one term that kind of looks the same as this one, but it's a little opposite. In order to flip it, I'm going to remove a negative and keep the other terms the same. This will make it 2x minus 1, because I can reverse the order of terms if I remove out a negative term. Now from here, we can, because we've already stated our MPVs, we can start canceling. So 4 over 2, I can cancel these out. This is going to become 2 over 1. There we go. I'll use a different color for my x's. I can cancel out my x's, and more specifically, I can cancel out 3 and 2 and write this as, instead of 2, I can write it, or instead of 3, I can write it as 1, because we're going to cancel out 2 of those x's. And then lastly, I'm going to get rid of these 2x minus 1s, because the 2x minus 1s I see as a common binomial. Therefore, this is going to be the following. This is a final answer equal to negative 2 divided by 1, which we don't really have to put. And then there was 1x in the numerator. So therefore, it's negative 2x is the final solution. And again, it is drastically important that you state your MPVs. Your MPVs are like the most critical piece of this problem. And I recommend that you're stating your MPVs always right as soon as you can. As soon as it's factored, state the MPVs, then do your cancellations from there. And maybe even just to show this, what I can do is I'm going to shift things around here. So let's say I take my answer, I move it just a slight bit down. I'm going to take my MPVs and I'm going to quite literally just insert them right between these two steps because I don't want you getting confused with the idea that MPVs must be stated before you cancel. Okay, now let's say we go over to part B here. So what I'm going to do is I'm going to look at these and be like, what variables are ones that I could combine together or bring together? Well, I don't necessarily want to start multiplying terms together to make big numbers. So what I'm going to do is I'm going to cross compare and eliminate things as I can in this form. But what I need to state is my MPVs. They all come from the denominator here when we multiply. So we're going to say the NPVs, and maybe what we'll do is we'll even write it off to the side here. We are actually, no, I like it over here. We'll put NPV is where A, B, C, and D all cannot equal 0. If any of those variables are 0, what it's going to do is it's going to cause the denominator to go to 0, and we can't have that. Now what we can do is we can start our simplification process. So what I'm going to do is in the problem, I'm going to go 5 divided by 40. This is the same as going 1 over 8. And then I'll try and make that 8 as neat as possible. I know my 8's kind of looped a little bit. There we go. And then what we're going to do is we're going to cancel our a squareds. Our a squareds become a squared divided by a cubed in the denominator. That's going to totally cancel the 1 in the numerator and leave us with one of the a's down in the denominator. For my other terms, I can then move on to my numbers and be like, well, 35 divided by 14, they both divide by 7. This is going to be 7 for this one. Or if we divide them both by 7, this should be 5, my apologies. And then this one would be 2, dividing them both by 7. And then now what we want to do is move on to our b's. We have b cubed, b1, that's b4. b4 divided by b squared, that leaves us with a b squared in the numerator. And so I can wipe out those terms, and maybe I'll just demonstrate that in the answer. And so we'll start off by writing 5 here in the numerator. As such, I'm going to divide by. In the denominator, we were left with 2 times 8 here because we had the we had the 8 that was a reduction from the 40. Now what I'm going to do is I'm going to do my a's. I was left with 1a in the denominator. I was left with b squared in the numerator. Now I want to move on to my c's. I have c4 divided by c1, and c1 brought together is c2. So c4 over c2 gives us c2 in the numerator by the quotient law. And then lastly, I just have that 1d down in the denominator, so I'm going to leave it exactly where it is. Now we just want to take that one step further and be like, okay, well, if we end up multiplying this out, it's going to be 5b squared c squared divided by the 2 times 8, which is 16, a times d. And there's our final answer. And again, if you just started canceling and you didn't state your MPVs, you're clearly going to miss the fact that b and c also could not equal 0. So be very, very careful with that. All right, now let's go down to part C. Part C, the nice thing is it's already in its factored form, so this is really good for us. We can state our NPVs right off the rip of this. So what we're going to do is we're going to say NPV, where R cannot equal, and the two options in which R cannot equal are where it's 1 and where it's -5, because either one of those would cause our denominator to become 0. If you plug in 1 here, it's 1 minus 1 is 0. If you plug in -5, -5 plus 5 is 0, so both of those would eliminate. Now what we want to do is do our reductions here. We can cancel out our r minus 1s because those are common between the two numerators and denominators. We can cancel one of the r5s because we have 1 in the numerator, 1 in the denominator at least. And then with the m and m1, we can bring these together to make them m cubed. So your final answer would look like the following. It's going to be m cubed, because m2 and m1 come together to make m cubed. And then we have r plus 5 as our final answer. There it is. Now, this doesn't have a denominator, which makes it even more important that we stated our MPVs before we did our cancellations. Okay, now from here, we're going to go over to part D. When we look at this one, it's not in its factored form. So let's start off by just factoring this thing. What I'm going to do is I'm going to write this is equal to, in the one numerator, let's get rid of that piece here. In the one numerator, I'm going to write this is equal to, we have y plus 3 and then y minus 3. We recognize this as a difference of squares when it factors. In the denominator, what we have is we have r, sorry, I'm going to make sure I have an r as a factor, which leaves us with r squared minus 1. Hey, look, that uncovered another difference of squares, which we'll talk about in just a second. I'm going to multiply this by r times r minus 1 if I factor that numerator, and then divided by y plus 3. Now, just as mentioned, when we factor out an r from this denominator here, what we realize is that we can actually factor it again. So what I'm going to do is write this as the following. In the numerator, still y plus 3 and y minus 3. In the denominator, instead of r and then r squared minus 1, it's going to be r plus 1, r minus 1. And then this is going to be multiplied by r minus 1, all over the y plus 3. Okay, here's where we state our MPVs. So I'm going to do that off to the side here. MPV, we have where r cannot equal plus or minus 1. That's our first MPV. Our second MPV is where r cannot equal 0. Now, let's just point out where these come from. If r is 0, it's going to make the whole denominator 0 because that would multiply to everything and make this 0. The plus or minus 1 comes from the idea that we have r minus 1, r plus 1, so it can't be plus or minus 1. And then our last MPV is where y cannot equal negative 3. Because if y equals negative 3, then that whole term goes away, and we don't want to have that term go away or that denominator go to 0, or else this will be undefined. Now what we can do is to get our final answer, let's do our cancellations. So y plus 3 we see is common. We see an r that's common. We see an r minus 1 that's common. And with all those terms being said that they're common, this is going to be equal to y minus 3 in the numerator divided by, whoops, I'm going to make sure that's a little bit better, divided by r plus 1. There we go. So this is our final answer. No more reductions, and as long as we have our MPVs as part of the solution, we're totally happy with this. Awesome. Okay, let's push forward into example E. Now, this one's a little more involved. The factoring is a little more complex than just difference of squares. So let's take a look at this one and say, well, first of all, what we want to do is, in this type of problem, what you could do is actually just split it up, and you could do all the factoring off on the side and then bring it back to the problem. I've seen that done successfully. I'm just going to factor within the problem here. But if it was a lack of space, definitely like try to utilize different areas of the page and be like, hey, maybe you do the factoring off in the margins and then you bring it all together in the problem. Now, for this first one, we need to multiply to make negative 12 and add to make negative 1. The factors that do that for me are x minus 4 and x plus 3. Divided by, we recognize this is a difference of squares, where it's x plus 3 and x minus 3. This is all going to be multiplied to, in the second fraction here, we have multiplies to make 3, adds to make negative 4. The two terms that will do that are x minus 3 and x minus 1. And then in the denominator, the other one, we're going to have where if I pull out an x, this leaves me with x minus 4. So there is my fully factored form. Now, again, we want to state our MPVs, so we're going to sandwich that right in the middle of our steps here. I'm going to write that x cannot equal, if it's plus or minus 3, it's going to eliminate those first terms. If it's 0, it's going to wipe out that third term here. And then lastly, we want to make sure that x is not equal to 4, because if it's equal to 4, it's going to wipe out that final binomial and make it 0. Now from here, what we're going to do is we're going to do our cancellations. We've stated our MPVs, so I'm going to go x plus 3 is common, so that one's gone. X minus 3 is common, so I'm going to get rid of that one. We have x, let's see what else we have. X minus 4, those ones are the other ones that are common. And so our final answer is just going to be x minus 1 over x. Perfect. And again, as long as we've stated our MPVs, that's the other half of the solution we're looking for, and we want to be very exact with that. Okay, now we're going to go down to our hardest problem of the part 1, which is this one here. And again, what we want to do is we want to look at this and be like, okay, it's a lot going on, but we're going to factor it. Maybe we factor it in the margins. Maybe we factor it. Maybe we factor it all together at the top, and then we just put it all together in the answer. That's probably the direction I'm going to go with this. So what I'm going to do is I'm going to do all 4 parts of factoring, and I'm going to literally label them 1, 2, 3, 4 right at the very top here. So let's start off with our first factoring part, which is a squared plus 2ab and then minus 15b squared. Now, don't be thrown off by the double variable. Essentially, to factor this, we're still going to do the same inspection method. So what multiplies to make negative 15 adds to 2. The two things that can do this for me are when a plus 5b and a minus 3b. And all we do is, if it's inspection and we have that second variable in the equation, just pair it with the second piece of the binomial. So whatever the number is here, pair it with that. Whatever the number is, pair it with that. Done. Okay, so there's our first factored form, and what we're going to do is we're going to highlight it in blue, indicating we want to bring this forward into the next part of the problem. Now, for step number 2, we're going to do that right below. Step number 2 is to take the denominator of that one, which was 3a squared minus 33ab, and then plus 84b squared, and put it together. Now, in any sort of factoring problem, we always want to make sure that we're factoring out a greatest common factor. In this situation, this is going to be equal to 3a, and I want to put the 3 on the outside, a squared minus 11ab, and then plus 28b squared when we divide 84 by 3. From here, we can then do inspection and keep that 3 on the outside. This is going to be what multiplies to make the 28 and then adds to make negative 11. The two terms that can do that for me are when a minus 7b and when a minus 4b, aka negative 4 and negative 7 are the two numbers, and therefore we're going to highlight this and say this is the denominator we want to bring forward. Now, as promised, let's just continue our factoring at the very top here. What we're going to do is for step number 2, we're going to take the numerator of the second one, or step number 3, I should say. We're going to take the numerator of the second fraction. So this is negative a squared plus ab minus 12b squared. In any sort of problem, we want to see if we can remove a greatest common factor. In this situation, it's negative 1, which leaves us with a squared minus ab plus 12b squared. Now we need a number that multiplies to make 12, but then two numbers that add to make negative 1. The two numbers that do this for me are positive 4 and negative 3. So I'm going to write this as a plus 4b and then a minus 3b. Perfect. There's our next factored form. Lastly, for step number 4, we're just going to take the denominator of the other term here. So part 4, we're going to go to this and be like, they gave us 2a squared plus 16ab and then plus 30b squared. Now, our idea is we want to pull out a greatest common factor, so I'm going to write this as 2a squared plus 8ab, and then 30 divided by 2 is plus 15b squared. The two numbers that can multiply to 15 and add to 8 are going to be where a plus 5b and a plus 3b. There we go. Highlight this. That is our final factored form. Okay, that's a lot of work, like a lot of work to factor this thing. This is a very standard of excellence problem, especially with this much being applied. So we factor all of these different trinomials. Once we factor them all, these are the terms that we're going to substitute in as those factors or as those sorts of fractions. So let's do that together here. Right below here, I'm going to just start subbing them in. So we're going to write this is all equal to, and now I'm going to write out our first term, which was a plus 5b, and then multiplied by our next term was a minus 3b. In the denominator of this term, we had 3a minus 7b and a minus 4b. There we go. And I'm going to put a big bracket around all of this to indicate that this was our first given fraction. Our second fraction started off with negative 1, a plus 4b, close the bracket, a minus 3b. Just to double check it's a minus, I'm going to scroll up a little bit. Yep. Divided by, in the denominator, this is 2a plus 5b, and then a plus 3b. Close the bracket. There we go. So here it is all put together. Now, whoa, this is a lot. What we want to do is, in the problem, they specifically said, let's just ignore the non-permissible values, meaning we don't really care what the a is in relation to the b or what the a cannot be in relation to the b, such that this would make it 0. We're just going to ignore that. Another reason you might say we might ignore this is because realistically, there's so many conditions around what a could not equal in terms of b that it's not going to make the biggest difference. The biggest thing we wanted to focus on was, can we factor this appropriately? Can we cancel this appropriately? And I know that kind of goes against a bit of the logic we used from before, where we said NPVs are so critical, but for this problem, we're just going to say, hey, you know what? They don't matter for now. Now, once we know our NPVs don't matter, the step we want to tackle is then canceling terms. So I'm going to go one by one and be like, if I know that a plus 5b cancels, let's cancel it here. If I know that we have an a plus 3, let's see if we have an a plus 3. No, we don't. What about an a minus 7? It doesn't look like we have that. An a Let's see if we have any other pieces here that can cancel. So the a minus 4 doesn't cancel. We have an a plus 3 that doesn't cancel. Let's see an a minus 7b that doesn't cancel. Okay, so this is going to give us quite a lengthy thing. What I want to do is just double check all my terms here. So for part 1, we had what multiplies to make 15, negative 15, and adds to 2. Yep, 5 and negative 3, which we have here. Great. Part number 2, which was our 3a, we factor that out and we get negative 7 and negative 4. Yep, that seems good for us here. Our next one, which was negative, we factored out the negative, which makes this negative 4. Oh, that's the issue here, is we got to change this because we have to add to make our, we have to add to make a negative in the middle. This one right here, this should actually be a positive, or sorry, a negative, and this one over here should be a positive. I knew something seemed just a tad off here. So what we're going to do is we're just going to erase this out as best as we can and then just redo that highlighting. So here we go. Perfect. Now it should be correct. And then we just have to go and edit this here. In the terms here, what we're going to do is wipe this out and this out. This is going to be A, and let's make sure that's actually the right tool here. A, this is going to be plus 3, and this is A minus 4B. And let's just make sure that's a little neater there. There we go. Now we should be able to cancel more of these terms. I was going to say something didn't seem a little right here. Now, let's cancel these two. Let's cancel the a minus 4 here. Let's cancel the a plus 3 and the a plus 3. Now what this is going to leave us with is we have this negative. So I'm going to write one more step here. This is equal to, we have negative a minus 3b in the numerator of the first term. And then in the denominator, we have this is equal to 3 times the a minus 7b times 2. 3 times 2 is 6. Our two binomials, or the one binomial left behind, is a minus 7b. So there's our ending term here, and that looks a lot better. If we were to be left with multiple binomials, it's not uncommon. It's just that like it wouldn't have been fully simplified. So again, that's why I always say just be careful with your factors, because as you can see, it's very easy to make a mistake on these, especially with signs. And as you're moving very quickly and you're factoring through these, you could see that I made a mistake right here, and it nearly cost me, because the fact that I had opposite signs here meant I wouldn't have been able to cancel two of these binomials. So just be very careful with that. Okay, now with the assignment practice, you're going to want to do some of these and really get in the swing of factoring again, and factoring in high repetition, because as you see, when you get to a problem like this, you may have to factor 2 or 3 or even 4 times like this example here. Now, let's move into part 2, and part 2 is going to focus more on dividing, and specifically the rules around NPVs when we divide, because everything's generally going to seem very familiar, just slightly different here. So, non-permissible values in division. Well, let's consider the following. If I have a over b divided by c over d, where these are both rational expressions and a, b, c, d are all variables. For the rational expression a over b, the non-permissible value for this one would be that b cannot equal 0, because if it's the denominator term, our denominator cannot equal 0. Similarly, if I have c over d, the non-permissible value would be that d cannot equal 0. Now, if we end up inverting this, or we do the reciprocal, where we go a over b divided by c over d, and we change it instead from division to then multiplication, what we need to focus on is that when we do this division to multiplication, it causes the c and the d to become a reciprocal, meaning that the c value also cannot equal 0, because now it's in the denominator. So we need to be very, very careful with this when we're figuring these out in terms of rational expressions. When we divide, we must consider the non-permissible values attached to the following variables or the following positions: denominator, denominator, and the numerator of the second fraction. So any non-permissible value will occur when it's present in the denominator at any stage in the simplification. And if you want to highlight that line, it might be really important, because denominators occur in multiple stages when we talk about division. Now, let's do a quick check your understanding based on this concept. So how many non-permissible values of x are there for the rational expression? Well, in this situation, again, let's bring out our purple highlighter. We need to consider the denominator here, and the numerator here. Because as soon as we see that division that occurs in the middle of these two things, we got to be like, we got to be on high guard and look at all these positions, because they all considered to be in the denominator during the simplification. Now, that means that our x cannot be equal to, and maybe I'll even formalize this and say NPV is where x cannot equal 2. Let's start off with the very first one. If I isolated for x in the first bracket, it would mean that this is going to be negative 3 over 2. The next bracket from that, if x equals negative 2, the whole bracket goes away. So I'm going to write negative 2. If I go to my numerator of the second fraction, it's where x cannot be 0, where x cannot equal positive 3, and then lastly, where x cannot equal negative 6. If x is any of these values where it gets substituted in for the purple brackets here or the purple terms, it would cause this to go to 0, which means that it would become undefined, which is exactly what we don't want. Okay, now for this one, the division of rational expressions. First and foremost, factor, just like we've done before. Factor the numerator, denominator, make sure they're simplified in factored form. State all the non-permissible values. That must be done right away. Before you do any sort of cancellations or any other operations, double check the non-permissible values. Insert the divisor and multiply. So what we can do is we can do our kiss and flip rule or the kiss and reciprocal rule. Change it to multiplication, do the reciprocal of the fraction. And then if there's any common fractions and we've stated out our NPVs, we can then reduce. And then lastly, just multiply and bring the terms together from the numerator to numerator, denominator to denominator. And if possible, then just factor further or reduce further from there. And again, keep our answer in the factored form for binomials. The reason is because when we look at our answer, we want it to be looking at it from the idea that this was its fully simplified form where everything was canceled nicely. Now, let's take a look at example 1 where we're going to look at a quotient in its simplest form and what are the non-permissible values. Starting off with a couple monomials together, what I'm going to do is just to make this a little nicer, I'm actually going to bring this y to the negative 2 upwards like this. And the reason I'm going to do that is because I know that y to the negative 2 is the same as, and I should write it as this, 1 over y to the negative 2 is the same as saying y to the positive 2 in the numerator. So I'm going to bring it up there and make this a rational expression. Otherwise, I wouldn't consider this rational. So this is xy squared. And then divided by, in the denominator, I'm going to go 2 cubed is 8, x cubed, and y cubed. And then realistically, I won't need that bracket anymore. This is going to be multiplied by, because I took that y and I brought it up and made this y cubed instead, I'm going to bring my 4x4 to the numerator when I do the reciprocal. And then I'm going to divide it by, let's make sure I write this out here, 4x4 divided by, in the denominator, this is going to be 21y to the power of 3, not 4, but 3. And the reason I did this is because if I already had a y here and I combine it with the y squared, this becomes y3. And then you're probably wondering, why did it go to the denominator? Because we moved it from the divisible factor, or it being divided, into now being multiplied. And as soon as we go from division to multiplication, we take the reciprocal of the second fraction. Now we can do all our reductions here. So realistically, I mean, you could multiply the numbers if you wanted to, but I think it's just better just to start reducing it from here. Before we reduce, let's just double check our NPVs. Our non-permissible values are going to be the following. X cannot equal 0 and y cannot equal 0. As long as both of these are non-zeros, we're like, yep, we're good with this. We're totally satisfied. Now, I'm going to go back and do my cancellation. So first and foremost, let's cancel our numbers here. If I take 7 and I divide it by 21, this is the same as 1 over 3. If I take 4 and I divide it by 8, this is the same as 1 over 2, or 1/2. And now what we can do is we can do all our variable cancellations here. This is going to be equal to, we have in the numerator 1 divided by, and it's going to be 2 times 3 in the denominator, which is 6. Now I'm going to go x times x4, which gives me x5. x5 divided by x3, that's 5 minus 3, which gives me x squared in the numerator. And then in terms of the y's, let's quickly do this. Y squared divided by y3 and y3. y3 and y3 multiply together to make y6. y6 then underneath y squared, that's y2 minus 6 gives me y to the negative 4, which would end up putting the y down here as y to the 4. So as a final answer, you could write this without a 1 and write it as x squared and then divided by 6y to the power of 4. There's your final answer. So when you're doing these rational expressions, realistically, I mean, you could bring them together and you could multiply them and make them one term. So you could be like, it's x5 and then in the numerator y squared, and then take it from there. And maybe even just to show that, we can do that. I'm totally fine with doing this. If we wanted to combine it at this step and be like, hey, this is x5 and y to the power of 2 divided by 2 times 3, which is 6. And then this is x cubed, y to the power of 6. And then you did your cancellations from here. Totally fine. That would be a-okay with me. I sometimes will skip that in class, but if you do that, excellent. That's showing all your work. It looks great. Okay, let's move on to B. B, the nice thing is it's in its factored form as is. Really nothing we need to do here. The only thing I noticed that we might want to do is obviously take the reciprocal when we move this from division to multiplication, but I see that this term is kind of opposite of this in a way. It's in the opposite order. So what I'm going to do is I'm going to write it as the following. Let's rewrite this as a squared and then 3a plus b in the first bracket divided by, instead of it being b minus a, I'm going to take a negative out, make this 6, and then go a plus b. I'm just going to swap them. And sorry, no, not a plus b, but a minus b. There we go, because you flip the signs of b and a in that bracket. I'm then going to go multiply by, and we're going to do the reciprocal, 2a to the power of 4, a minus b, and then all divided by this term in the numerator, which was 3a plus b all squared. Now from here, let's make sure to state our MPVs. Our MPVs are going to come from the following three, and it's really important maybe to highlight this. I'm going to use the pink marker again. This term, and this term. These all decide the MPVs. So it's very, very important we're paying attention to these. Our MPVs are going to be the following. So we're going to write NPV. We need where A cannot equal B, because if A equals B, then this bracket wipes out, this bracket wipes out. The other value is we can't have an A that's equal to 0, because if A equals 0, then this term eliminates to 0, which we don't want. And lastly, if A, maybe we'll summarize it in terms of B. If B cannot equal negative 3a, that's because if I subbed in a negative 3a here, negative 3a would cancel the 3a's here. And again, to get these values, what you can do, and I'll just do this off to the side here, if I wanted this MPV, what I can do is, and maybe I'll actually just show all the steps of getting it, just so that you can see it. From quad equations unit, we took the given binomial, 3a plus b, set it equal to 0, or in this case, not equal to 0, and then we isolated the variable we wanted to. So I'm going to move the 3a across. This gave me b cannot equal negative 3a when I subtract it across, and that's the variable. Now, I could write it in terms of a if I wanted to. I could write it in terms of b. That's all okay. They didn't really specifically specify, so however you want to write that. Now, this is going to be equal to, when we do our cancellations, let's make sure we cancel things we can. So I'm going to go a minus b, a minus b. Those can go away. I'm going to cancel one of the a minus b's away from here because I have 3a plus b divided by 3a plus b squared. So I can eliminate one of the ones from the denominator and the other one completely from the numerator. This is going to leave me behind with the following. I have 2a squared times a4, which is 2a to the power of 6, all divided by, in the denominator, this is negative 6, and then it was left behind with a 3a plus b. Now, for some of you with the keen eye, you're going to look at this and be like, we can reduce this one step further. 2 divided by negative 6 is the same as 1/3, or negative 1/3. So I'm going to make this a to the 6 divided by negative 3, and then 3a plus b. There we go. And there's my term here. And I just want to neaten this up a little bit here. So this is negative 3, and then 3a plus b. There we go. There's the final answer. We want to reduce not only our fully factored form, but our numbers to go with it as well. Awesome. Okay, now let's go to our next page here. We're going to be given examples that kind of look like the ones we dealt with in part 1, just now with a divisible symbol in the middle, or a quotient symbol in the middle, meaning we're going to divide them. Now, when we divide them, first of all, we want to factor these. So let's factor them as, in the first one, it's a difference of squares, x plus 11, x minus 11. There we go. This is going to be divided by. We take the difference of squares of this one, which is x plus y, x minus y, because that's also a difference of squares. Now, I'm going to change this to multiplication. And when I change it to multiplication, this is going to cause the reciprocal to be x plus y in the numerator. And then in the denominator, it's going to be 11 minus x. Now, to make this 11 minus x match the term here, what we can do is we can actually take this and just pull out a negative from it. So I'm going to rewrite this as the following. This is going to be x plus 11, x minus 11, and then close the bracket, divided by x plus y, x minus y, And then this is still multiplied by, in the second fraction, x plus y. And then if I remove out a negative, now I can write it as the x minus 11 to match. Okay, let's state our NPVs very quickly before we do any cancellation. NPV, it has to come from the following spots: here, here, and here. It's all three of these. It's the trifecta, as I call it. Now, from here, we're going to write this as x cannot equal plus or minus y, because if it's plus or minus y, it will eliminate those terms. It also can't equal 11, because if it's 11, then therefore, it's going to cause this to be equal to 0. Okay, we now have our NPVs. Let's make sure we cancel out the terms we can. Our x plus y is gone. Our x minus 11 is gone. So let's make sure that those are all gone. What we're left with is a negative, or a negative 1 here, an x minus 1 in the denominator here, and an x plus 11 here. So we could write our final solution as the following. Once we've canceled, this is going to be equal to, we can write it as negative x plus 11, all divided by the x minus y in the denominator. And realistically, we don't need those brackets if we didn't want to, but I like having them in here. And lastly, this negative is transitive. So if you wanted to put it down here or out in front, I mean, those are all totally fine. I'm just going to write it in the numerator like that, and that will be fine. But just know that it could be in a bunch of different locations, including right out in front of the fraction, or it could be in the denominator, or it could be in the numerator where it is. Transitive means it can be anywhere from there. Okay, let's go on to this example here, part B. Part B looks all complex, but it's because they vertically stacked it rather than putting it horizontal. So I'm going to make this look just a tiny bit nicer. What I'm going to do is I'm going to write this is equal to, in the numerator, the first term is 3xy divided by 9x squared minus 12x. And then I'm just going to write it as divided by horizontally instead. 12y divided by 9x squared minus 16. Now, from here, you're probably looking at this being like, hey, we could factor this more, couldn't we? Like, this is not done yet. So what we're going to do is we're going to factor this. And I'm also going to take care of the reciprocal step at the same time. Actually, no, let's save that for a second. So I'm going to write this as 3xy, which is fully factored as is. We can take out a 3x of this one, leaving us with 2x, not 2x, but 3x minus 4. Because we divide both by 3, we also take off an x from each of them. Now I'm going to keep this as divided by, just for a second, 12y. In the denominator of this one, we're going to write it as, this is going to be 3x plus 4, and then 3x minus 4, because we recognize it as a difference of squares. Now we can do our flip step. So this is going to be equal to 3xy divided by 3x, and then 3x minus 4, multiplied by, in the numerator, 3x plus 4, and then 3x minus 4, all divided by 12y. Excellent. Now from here, let's make sure we do some sort of cancellation if possible. Actually, no, not cancellations, NPVs. So we're going to state our non-permissible values, where x cannot equal, first and foremost, it can't equal 0 because it comes from here. We also can't equal plus or minus 3 over 4, because if it's plus or minus, and it should be 4 over 3, my bad, plus or minus 4 over 3. If it's 4 over 3, then that will cancel out these terms here. So this one here or this one here. Lastly, we need to account for that y. We need to say that y cannot equal 0, because if y is equal to 0, it eliminates this denominator here. And again, when you're doing this division like this, you got to be aware that everything in the denominators at any point is considered to be fair game for the NPVs. So as you can see, we have these two in the denominator originally, and we're like, okay, we don't want to have those be 0. But then when it flipped to make this, now we have to consider all three of these as denominator terms, which clearly, if you look at this, if I drew a line right here under this, all of this is considered to be the denominator as written. So what terms are all three of these? It's these three terms here that make up the denominator of the original fraction. And so we got to be very careful. If any of those end up being 0, it makes the entire thing undefined, and we don't want to be in that situation. Lastly, let's just make sure we cancel out terms we can. So we're going to go 3 divided by 3 eliminates. We have an x divided by an x that eliminates. We have a y divided by a y that eliminates. We have a 3x minus 4 that eliminates. And then very lastly, this is going to leave us with the following. In the numerator, we have 3x plus 4, which is the one binomial left. And then in the denominator, we have 12. Now, you could separate this and make them their own fractions and then reduce them, but I'm going to leave it exactly as is. I'm happy with this as it is. Perfect. Okay, now let's move on to part C. Whoa, part C, this is a lot. We're going to want to factor this thing just like we've done in the previous problems. And once we've factored it, then what we can do is we can start to reduce after we state our MPVs. So in the first one, let's state this as 3x, or I'm going to let's factor out a 3. 3 and then x plus 4 divided by, in the denominator, this one doesn't have a GCF that can be taken out such that we can do inspection. So what I recommend you do is if you ever see one that you need decomposition for, maybe we take a second just to do that off to the side. So I'm going to move this just like over just a tad here, and we're going to do the decomposition for this second, or for this trinomial in the denominator as 3x squared and then minus 5x minus 12. We need two numbers that multiply to make 3 times negative 12, which is 36. 3 times negative 12 is 36, negative. And then we'll subtract to make negative 5. Well, the difference there, if we take numbers that multiply to make 36 and then add to make 5, that would mean that it is 3x squared minus 9x plus 4x and then minus 12. Now, when we factor by grouping, this is going to become 3x on the outside, leaving us behind with x minus 3. And I might have to move this over just a tad. I'm realizing that it's still not over enough in order to give us the space. So this will become this. Then we write this as plus 4, x minus 3 in our second bracket. And then when we pair them together, it's going to be x minus 3, which is the common binomial, and then 3x plus 4 for the second binomial, or the outside terms here. Now, because I don't want to make this seem kind of like the afterthought of the problem, what I'm going to do is I'm actually just going to start with this. I'm just going to make this step number one. If I see this, just like I said before, what you can actually do is take these terms and you can factor them originally off to the start here. If you factor them, here's what your factored form becomes for this first one. And then what we can do is actually start to work with it from here. So now I'm going to take this problem and be like, in the numerator, we can write this as equal to, there we go. So now we can write equals to, our first factor was 3, x plus 4 gets reduced, divided by, in the denominator, we're going to put this new factored form, x minus 3, and then 3x plus 4. There we go. Now we're going to divide this by, we had 12 all divided by 3x plus 4, and then multiplied by the factored form of this next one. We can remove out a 2 and make it 2x minus 3, and then divided by the x plus 4, which in this case, there's nothing we can do with this. Okay, now that we have it in this form, let's just do our reciprocal rule. We want to change this division symbol, or the quotient symbol, into multiplication, which means we take the reciprocal. So I'm going to write this as equal to 3x plus 4, and then divided by our x minus 3 and 3x plus 4. I'm then going to change this to multiplication, which I need to do a better job of that. There we go, multiplication, 3x plus 4 divided by 12, and then times the 2x, or 2x minus 3 divided by x plus 4. Now, let's state our MPVs, but we got to be very careful what we're considered to be the denominator. Well, in this problem, if we go back to the original, these were all the denominators originally, so we're definitely going to look at these. But we also need to look here as well, because if it's dividing or there's a quotient symbol, then these two are considered to be part of the denominator. And if you drew this out in a vertical stack, you would see that all of this could technically go below. So what we're going to do is account for all of that. And I'm just going to use some purple highlighter here to recommend that we need to pay attention to this. So here, 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 and here, these are all the important ones. And I just want to make sure that all of this is neat. There we go. These are all the ones we want to pay attention to for our MPVs before we cancel. We're going to go MPV, x cannot equal, and we're going to start off with going x cannot equal, 3 is the first one coming from our first binomial. Our second binomial is negative 4 over 3 as the solution for this one. If we look up to the numerator here, it's actually the same. Negative 4 over 3 would make that 0. And then lastly, if we look at our denominator from here, we see that x cannot equal negative 4, because if it equals negative 4, then it wipes out that term. Lastly, let's do all our cancellations here. So we're going to take away the x minus 3, because we see it occurring on a couple terms. X minus 3, x minus 3. We see x plus 4 and x plus 4 here. We see 3x plus 4 and 3x plus 4 here. So that wipes away this. Now what we have is we actually get a number of, in the numerator, this is going to be 3 times 2, which is 6, divided by 12. And 6 divided by 12 simply reduces down to 1/2. So it's kind of funny because in the end, we end up getting a solution that's just this nice number for such a messy overall solution with so many different polynomials, and we had to factor and we had to do all this kiss and flip rule and state the NPVs. You get 1/2 as the solution, which is kind of satisfying that it ends up working out to some sort of not whole number, but some sort of positive value in this case that is a fractional quotient. Okay, last problem we're going to want to focus on is this one here, is simplify this one. Now, this requires a ton of factoring. So what we're going to do is we're just going to work through this step by step. And what I might do is even combine some steps just to help us simplify this a little bit as we go. So this is going to be equal to, in the first numerator, I keep it as x plus 3 divided by what multiplies to make 15 and then adds to make -2. The two numbers that will do that for me are going to be 5 and 3. And we're going to make the x plus 5 the positive one and x minus 3 the negative one, because we want to make sure that that number, actually that should be opposite. We want this to be negative, this to be positive. So I'm going to put negative and positive because it has to add to make -2. I'm then going to flip this right away, and I'm going to actually make this the following. We're going to factor this term, the x squared plus 5x minus 14, multiplies to 14, adds to make 5. That makes it x plus 7, and then x minus 2. And then this is going to be divided by, if I factor out the 2, it's x minus 2. Now, this is multiplied by the next set, which if we look at this piece, we can factor out a 2, leaving us with 5 minus x. And then I can factor the denominator. This requires decomposition. So maybe off to the side, I'll do the decomposition here. We need it to be 2x squared plus 15x plus 7. It must multiply to make 14 and add to make 15. Well, the two numbers that do that for me are 14 and 1. So I'm going to write it as 2x squared plus 14x plus 1x plus 7. I factor by grouping, which I take the 2x out of the first, leaving me with x plus 7. I take positive 1 out of the second grouping, leaving me with x plus 7. And now what I can do is pair together my outside terms, 2x plus 1, and put one of the common binomial, 2x, x plus 7, I should say. Now, that's going to be what we place down here. So this is going to be 2x plus 1, and then x plus 7. There we go. And maybe what I'll do is I'll even highlight this in blue, just as we've done before when we factored it off to the side. And then I'll just arrow that into the problem here, indicating that that comes and joins in here. Now, from here, we need to state our NPVs. So I'm going to state them below. NPV. We're going to state where x cannot equal 2. First and foremost, it can't equal 5. It can't equal -3. It can't equal +2. It can't equal -1/2. And then it can't equal -7. Is there any other ones we're forgetting? Potentially, actually, the one that is in our numerator here. And the reason is we got to account for this one here because the original was a quotient. When we multiplied it, it was the reciprocal. So it actually was in the denominator. We need to make sure we include -7, which we did. We need to include +2, which we did. Okay, great. Those have both actually been accounted for. And you know what I'm even going to do? I'm going to highlight these in purple to indicate that these are the ones that we had to pull the NPVs from, just as a way to make sure that we have captured all of them here. Perfect. So now we have our NPVs. Let's see if we can do some cancellation. The only thing that I'm going to potentially do here is I'm going to change the order of the numerator one. Instead of this being, and maybe I'll just write it as a side note here, because I feel like if I go back and erase it here, it's going to cause too much confusion. Let's say I change this. I can make this into -2 and then x minus 5 instead. If I wanted to, I can just flip this by taking out the negative. Now, this is going to save me a lot of headache rather than having to rewrite it all, because now what I can do is be like, well, I see my x minus 5s are common, so maybe I take my x minus 5s out, where these are my x minus 5s. I can cancel out my x, let's see, x minus 2s are common, so let's remove those. I see an x plus 7 is also common, so I'll remove those. Do I have an x plus 3 in common? No. Do I have a 2x plus 1 common? No. So those ones stay behind. And therefore, I need to make sure that I keep the negative from here. So that one is going to be negative. And then I also want to make sure that I keep my 2 in the denominator with the 2x. So let's write out everything that I have left behind after canceling this. I'm going to have in the numerator negative 2 because of the n term here, negative 2. And then I'm going to write this as x plus 3, which was the binomial left behind, divided by, in the denominator, there was also another 2 and 2x plus 1, meaning we probably could have canceled our 2's in that previous step, but let's just do that now. We're going to cancel out the 2, cancel out the 2, and that's just going to leave us with that negative that can be transitive here. So this is going to be equal to, we're going to have negative x plus 3, and then divided by the 2x plus 1. Now, again, are the brackets really necessary for the most part? No, but I mean, they just help you organize the fact that these are binomials. This is what the final solution was left as, and we want to keep it as this. All right, here's where you're going to want to go into your assignment. As you can see, these are factor heavy. If you can factor in this unit, you will be an expert at this unit. You just can't forget about your MPVs and where to find the MPVs. That's very critical. But if you're a factoring pro, which many of you are actually, I've seen this in your work in chapter 0, if you can factor, you can do this unit very successfully. All right, get a ton of practice around 6.1 and 6.2. That was a long lesson, but hopefully you've gained a little bit of skills out of this in terms of not only your factoring, but just some of the little nuances that might pop up in these problems.